So, welcome student to the next class of Introduction to Nonlinear Optics. In the previous class, we learned about the cross phase modulation and then study the nonlinear absorption. So, today we will have the lecture number is 49 and we will have in our lecture today one important concept called four-way mixing and then learn another thing called crosstalk frequencies. So, what is four-way mixing and crosstalk frequency? Let us start. So, four-way mixing is an interesting phenomena in nonlinear optics. So, what is the meaning of four-way mixing? Let us try to understand. So, here the definition or the idea of the four-way mixing is written. So, four-way mixing is a nonlinear effect arising from third order nonlinearity as described with a chi3 coefficient. So, if our chi3 coefficients are there in a system, what happened? The nonlinear polarization will be coming as a function of E cube. So, it will be E, E and E, there will be 3 E related to that term. Now, if two frequencies are there, at least two frequencies are there, omega and omega 1 and omega 2, maybe more than two frequencies there, we will see that. Then these two frequency omega 1 and omega 2 can combine themselves to generate another two frequency omega 3 and omega 4 in this fashion. If omega 2 is greater than omega 1, then additional frequency component as shown in this figure 1, the additional frequency component omega 4 and omega 3 can be generated. So, let us try to understand this. P nonlinear is equal to epsilon 0 chi 3 and two waves are there. So, that means E 1 omega 1 plus E 2 omega 2 is there. Obviously, the complex conjugate will be added with that and then we make a cube of that. Once we make a cube of that, so there will be a different kind of frequency mixing. So, we will have 3 omega 1, we will have 3 omega 2, we can have minus of 3 omega 1, minus of 3 omega 2, the complex conjugates of that two term and also the combination of these two. So, one combination may be E 1 square E 2 star. So, E 1's it is so E 1 square E 2 star basically give rise to one frequency 2 of omega 1 minus omega 2, which is this one. So, this combination basically give rise to a frequency omega 3 and also another combination can be possible, which is E 2 square E 1 star, which give us 2 omega 2 minus omega 1. So, another frequency is there. So, we start with two frequency omega 1 and omega 2. The combination of these two omega 1 and omega 2 can give rise to two different frequency. One is this omega 4 and another is this. And the relationship between this frequency is something like this. If you write these things here, then we can write a more simpler expression and this expression is omega 4 minus omega 2 is equal to omega 2 minus omega 1. So, if I have a difference here delta omega, which is the difference between omega 1 and omega 2, then I can generate a similar kind of frequency beyond omega 2 with addition of delta omega and also another frequency with delta omega frequency less than omega 1, which is the lowest frequency. So, we have a frequency omega 1 and omega 2 is greater than omega 1. So, if I make a difference between omega 2 and omega 1, we can generate omega 4, and if we also generate another frequency this side with omega 3 with this relationship. So, this is essentially called the 4-way mixing, because we are basically mixing 4 different waves, or the 4 different waves are generating, omega 1 and omega 2 are there, and then we generate another 2 wave omega 3 and omega 4. By the way, there are different kind of possibilities are there. This is one specific possibilities I am talking about, and in this case, if omega 1 and omega 2 are already there in the system, so what happened that we can able to amplify this signal. So, this is called some sort of parametric amplification. So, parametric amplification for second order effect we have already discussed. So, this is a different kind of parametric effect under 4-way mixing. So, that we will going to discuss. But the thing is, if I launch 2 wave omega and omega 2 in third order under third order nonlinearity, there is a possibility that it will going to generate 2 different frequency omega 4 and omega 3 with following with this relationship with the same frequency apart. Well, next we will try to understand this in detail. So, first the degenerate 4-way mixing. In degenerate 4-way mixing, as I mentioned, omega 1 and omega 2 are used. They are used twice, because when I calculate this omega 4, you can see here I use 2 omega 2 and 2 omega 1. That means omega 2 plus omega 2 minus omega 1. So, I use 2 different. So, in input I have omega 1 and omega 2. When I generate omega 4, I am using omega 2 twice and omega 1 once. So, that means this is a degenerate case. But more general is non-degenerate case, which is shown in the right hand side. You can understand easily that if instead of launching 2 waves, if there are 3 waves in the system, omega 1, omega 2 and omega 3, which are not equal to each other as shown here, then there is a possibility that they will going to generate a combination of all these 3. So, omega 4 will generate, and omega 4 will be the combination of all these 3 frequencies. So, plus minus omega 1, plus minus omega 2, plus minus omega 3, this 8 different, there will be 8 different combinations. So, 8 different combination one can generate. So, here the p nonlinearity term shown how this from p nonlinearity term how this frequency mixing is happening because of the launching of 2 waves, one is omega 1 and another is omega 2. But in this case we are launching omega 1, omega 2 and omega 3. When I make a cube of that, you will have 8 different combination. If omega 1, omega 2, omega 3 are distinct, they are not same, mind it, they are not same, that is why it is called non-degenerate 4-way mixing. So, we have a degenerate 4-way mixing, we have a non-degenerate 4-way mixing. In non-degenerate 4-way mixing, if omega 1 and omega 2 are same, then it will just convert to degenerate 4-way mixing. So, degenerate 4-way mixing is a special case of non-degenerate 4-way mixing, where 3 waves are mixed to generate a 4th wave, but if these 3 waves are not identical, if not distinct, if they are 2 of them are identical, then we will have a degenerate 4-way mixing and we will get some specific frequencies with that. Okay, once we have the idea of degenerate and non-degenerate frequency, so let us try to find out how mathematically we can understand that, or how the treatment is done. So, for non-degenerate 4-way mixing, which is a most general case, omega 1, omega 2, omega 3 is launched, and as a result I am generating omega 4. So, the 4 waves can be represented in this way. So, E of omega 1 is a wave of omega 1, it is half E1 e to the power I propagation constant k1 omega 1 t plus complex conjugate. This is the standard way, the plane wave form to represent a wave. We are We have been using this for last almost all classes. I am using this notation. So, in the similar way I can write the electric field for omega 2, omega 3 and also generating field omega 4. So, inside the system, if I want to find out how omega 4 is generating, so what we need to do, that there are 3 waves here. So, these 3 waves I write this plus this plus this, that is E omega 1 plus E omega 2 plus E omega 3, and if I make a cube of that, as I shown in the previous slide, that there will be a combination of these frequencies, because complex conjugate terms are also there. So, omega 1 is there, so minus omega 1 is also there, omega 2 is there, minus omega 2 is also there, omega 3 is there, minus omega 3 is also there. So, now if I write this 6 term, essentially there are 6 terms, omega 1, omega 2, omega 3, here we have omega 2, this again make a mistake. So, if I have 3 terms, then essentially the complex conjugates are also there. So, 6 terms are there, and if I make a cube of that, and if I consider omega 1, omega 2, omega 3 are not same, then we will have a combination of omega 1, omega 2, omega 3, and this combination give rise to a 4th frequency called omega 4, which is plus minus omega 1, plus minus omega 2, plus minus omega 3 in general. It may be plus plus plus, it may be minus minus minus. There will be 8 different combination one can expect. Okay. So, next let us try to find out some example of non-degenerate 4-way mixing. As I mentioned, there will be 8 combination of that, but from this 8 combination, if I take only one combination, that all waves are, all frequencies are added to generate omega 4, then this is a specific combination. So, mind it what we are trying to do. So, we find that omega 4 is essentially the combination of omega 1 plus omega 2 plus minus omega 3. There will be 8 specific combinations. If omega 1, omega 2, omega 3 are not equal to each other, they are not identical to each other, they are distinct, then from these we can take only one combination and try to understand what is going on. So, omega 3 is just omega 1 plus omega 2 plus omega 3. So, this is our frequency. So, the k vector can also be written in this way. So, in order to have the phase matching condition, we have the wave vector, the momentum matching in this way. The total electric field I can write in this way also. The total electric field of omega 1 plus omega 2 plus omega 3 plus omega 4, because all the 4 waves are now inside the system and I need to find out the differential equation of each individual fields. So, that treatment, in order to do that treatment, we need to take care of all 4 fields, and P nonlinear is now written is epsilon 0 chi 3 total field cube, where total field is the combination of 4 field which are generating inside the system. When I make the cube of all these things, then there will be different combinations one can expect, but mind it, our aim is to find out the frequency omega 4, which is the sum of all these things. So, from here we can readily find out what should be the nonlinear polarization component having the frequency omega 4, and we write it at P nonlinear in bracket 4. The bracket 4 suggests that we are taking the frequency component omega 4 here. So, how the combination one can get? So, omega 1 plus omega 2 plus omega 3. So, that means E 1, E 2, E 3, that is the amplitude of these 3 waves that should be multiplied. Exponential term E 1, K 1, K 2, K 3 will be there, and I will have a frequency component omega 4, because if I multiply these three things, then I will have a frequency component omega 1, omega 2 plus omega 3. So, this is essentially omega 4. Also the degeneracy factor one can consider. The degeneracy factor, we know that if these three distinct fields are associated to generate the corresponding polarization, then 1/6 multiplication should be there. So, here three fields are distinct. So, this 6 term will appear because of that fact, and also you remember here it is not written. So, already we have written in the previous slide that E of omega 1 is half of E 1 e to the power of I k 1 z minus omega 1 t plus complex conjugate of that. So, this half term basically gives rise to this 8. So, I have p nonlinear term in our hand, and if I manipulate the nonlinear Schrodinger equation for E4 term, so it will be simply this quantity. So, this is the nonlinear Maxwell's equation that we have been using to generate the evolution of different fields. So, for E4 fields, how our aim is to find out how this E4 or the field containing the frequency omega 4 will going to evolve. We will just use this nonlinear Schrodinger equation, nonlinear Maxwell's equation. So, this nonlinear Maxwell's equation basically gives a source term. So, we have already calculated this source term p nonlinear 4, which is basically give rise to this field omega 4, and then if you calculate the way we have been calculating the derivatives and making a derivative and then do all these things, you will come to this expression in a straight way, and then you will have an equation for electric field containing the frequency omega 4. This how these things are coming, if you do yourself, you will find out quite easily. It is already done here in these slides. I am not going to detail because this calculation is quite trivial, but the important thing is that the source term here, in the source term E1, E2, E3, which basically give rise to the field omega 4. But from that also you can all calculate the other fields, evolution of the other fields like E3, E2 and E1, because all these 4 fields are there. So, essentially we should have the evolution of other field also. So, now for other fields, if you look carefully, this term will going to change, and it should be, because once we find E3, the nonlinear polarization term will contain a term. So, omega 3 is, if I write this is my equation, then omega 3 is basically omega 4 minus omega 1 minus omega 2. This minus omega 1 and minus omega 2, let me write it once again. So, omega 3 suppose is equal to omega 4 minus, so let me write it, omega 3 is omega 4 minus omega 1 minus omega 2. So, if I want to find out the corresponding frequency component, the field will be E4, for this minus sign it will be E1 star, and for this minus sign it will be E2 star. This will be the combination of the field in p nonlinear, and if you look carefully, it is exactly the same thing we are having here for d E3 dz. In the similar way, d2 dz I will have a differential equation like this, and d1 dz we will have a differential equation of this. So, for 4 different fields I have the differential equation in our hand. Only for one cases I calculate the p nonlinear term for omega 4, but you can do that for other frequency terms, and you can calculate quite easily by just inspecting. I can calculate this, and this is basically the evolution equation under 4-way mixing, this is the evolution equation of 4 fields that is generating. Well, we can go further, we can have an example. Now we can have an example of degenerate case. For degenerate case, the equation one can also derive, but for degenerate case 2 electric fields is now associated, not all the 4 electric fields. So, these 2 electric fields can give rise to omega 1 and omega 2, that these 2 are the frequencies. This will going to generate a third frequency omega 4, and omega 4 is a special. From here we can see that omega 4 is 2 of omega 1 minus omega 3, this is a special combination. And for the special combination, once we calculate the evolution of the electric field corresponding to omega 4. So, I will have here the frequency component 2 omega 1 minus omega 3. So, the field should have E 1 square E 2 of star E 3 of star, sorry, because it is omega 3. So, this quantity, the phase term will come as usual. Only thing that you note that since E 1, E 3 and again E 1 is used, so that means there are no 4 distinct fields are associated with that. So, degeneracy factor will be not 6, but 3. So, when we use the degeneracy factor 3, so this quantity will going to change slightly. In the previous slide, if you look carefully, in the previous slide it was 3 by 18, but now it should be 3 by 16, because the degeneracy factor 6 here will be changed as 3, because I am making 2 same fields here to generate our P nonlinear terms. Well, now we will briefly describe about the crosstalk frequency. What are the crosstalk frequency? As I mentioned, there are several kind of frequency mixing can be possible. So, depending upon the individual frequencies, this is called the bit frequencies. So, some bit frequencies are such that they are very close to the launching frequency. So, because of that they can generate some kind of cross phase or crosstalk problems, and this is happening in optical fiber where WDM systems are there, wavelength division multiplexing process, where different frequencies are moving together as a different channel. But if the 4-way mixings are there, what happened that different frequencies component will going to generate, and from this different frequency component there are few frequency components which are very close to the launched frequency component, and as a result what happened, we will have some kind of distortion in the signals. So, here if you look carefully, so let us try to understand. So, we term omega I j k is equal to omega I plus omega j minus omega k with I not equal to k, j not equal to k. With this condition, we write this there is a specific frequency condition or the specific frequencies. Now, how many frequencies is possible if I j k are 1, 2, 3? There should be 12 different frequencies if I is not equal to j and j is not equal to k, I is not equal to k and j is not equal to k. So, I have 6 combinations omega 1 1 2, omega 2 2 1, omega 3 3 1, omega 1 1 3 and so on. So, these are the 6 combinations that we have, and another combination we also have if all these 3 frequencies are distinct. So, I, j, k are not same to each other. So, they will have another 6 combinations. So, this total 12 combination one can have with this equation if I change I, j, k as 1 to 3. So, as an example, what is the meaning of omega 1 1 2 frequency? What is the meaning of that? It means it is omega 1 plus omega 1 minus omega 2. This is the frequency I am talking about. So, here 2 frequencies omega 1 and omega 1 are same, omega 2 is different. So, I is equal to j here, but I and j both are not equal to k. That is the condition we have. But if I write 1 2 3 omega 1 2 3, it is simply omega 1 plus omega 2 minus omega 3, and here I j k all are different, and this is another combination of the frequency where these three frequency are non-degenerate. So, degenerate condition and non-degenerate condition, both conditions are there, and based on that we can have 12 different frequency. If I define my frequency in this way, why we are defining this frequency in this way, we will try to understand that, because this frequency will give rise to some frequencies which are very close to the launching frequency. This is a very important figure, and if you understand then figure, then you will readily understand what is the meaning of cross talk frequencies. So, our frequency definition is this, that is omega I j k is omega I plus omega j minus omega k. Omega 1, omega 2, omega 3 is the three fundamental frequency that is launched into the system, where the spacing between omega 3 and omega 2 is delta omega, and omega 2 and omega 1 is delta omega. These are the spacing between these two. If this is the case, then I will have 12 different frequency combination, and in this frequency plot, if I plot these 12 different frequencies, then it will be plotting, one can plot in this way. So, first let us try 1, 2, 3, this block, these shaded frequencies are the fundamental frequencies, and from these fundamental frequencies I can generate omega I j k, which is a combination of these frequencies. So, how many combination we have in the previous slide? It was 12. So, I can see that there are 12 frequency. If I start from here, this is 1 frequency, this is 2 frequency, this is 3 frequency, this is 4 frequency, this is 5th, this is 6th, 7th, 8th, 9, 10, 11 and 12. This 12 frequency will be distributed in the frequency location in this way. How these things will be distributed, let us try to understand quickly in our last slide. So, this is the matrix of the frequencies, and now we try to understand how this frequency are located. For example, let us start with omega 132, this frequency. How these frequencies are generating? Omega 132 is essentially omega 1 plus omega 3 minus omega 2. Now, omega 3 minus omega 2 is means this is this delta omega. So, I write this as omega 1 plus delta omega, because delta omega is the spacing between omega 3 and omega 2. So, this omega 1 plus delta omega means this is my omega 1, and if I add delta omega, this frequency basically fall on here on top of omega 2. So, omega 2 frequency is nothing but omega 132 frequencies. The combination of these three frequency basically give us a frequency which is omega 2. So, if omega 1, omega 2 and omega 3, these three frequency are, the difference between these two frequencies are close enough, or if they are not exactly same but very close enough, then what happened that this frequency omega 132 will fall very close to omega 2 frequency. Now, it is falling exactly on omega 2 frequency, because we consider this delta omega same for both the cases. If they are not same but close to each other, then what happened, this omega 132 frequency will fall exactly or very close to this omega 3 frequency, and that basically creates the problem of crosstalks. You can do for all other frequencies by yourself. Here few examples are shown. For example, omega 223 is omega 2 plus omega 2 minus omega 3. Omega 2 minus omega 3 is minus delta omega, and it is subtracted from omega 2. So, essentially it leads to a frequency omega 1. So, it will fall on omega 1. In the similar way, you can calculate that omega 2 1 3 frequency 213 will give rise to omega 1 minus delta omega frequency, and also omega 1, 2, 3 frequency give rise to omega 1 minus delta omega frequency, which falls in this side of omega 1. So, right now we like to conclude because we do not have much time. So, today you have learned a very important concept. One is 4-way mixing. So, we will learn more about the 4-way mixing in the coming classes and also learn a specific example of crosstalk and how this crosstalk create the problems we discussed, and how this crosstalk frequencies are generated also, that is discussed. So, with this note, let me conclude the class here. So, in the next class I will discuss more about the 4-way mixing. So, thank you for your attention and see you in the next class.